Oh, GM. I, I would live. Okay, looks like we're live. Let me confirm. We're actually starting a bit late. Share screen. Let me see. All right. Yeah, everyone. So today we'll be talking about uh, Alpenglow. What is Alpenglow? And we'll be doing a deep dive into how it works, just for like an hour or something. We'll be reading the white paper and just going over everything step by step. Let's see how far we can cover today. So let me bring this up. Okay, let me see. Oh my gosh. Uh, okay, so let me share this. Okay, sharing this. Yes, this is what I was looking for. So if we go over here, yeah. Okay, so 1 minute, still not there. Yes, this is what so I'm talking about. So what's helping glow? This is the question. So let's get to first part of it. Let me put it up a bit. This it says I don't read off exactly what's on the book. It's a consensus protocol for it's like an upgrade for the way the consensus is done on Solana. It's a proposal for how consensus is done on Solana. So that's basically what it is. If you read over here, the abstract says there are two major components. It's replacing the first part is replacing two major components, which is the voter and the rotor. And what does all of this even mean? So yeah, it's a better way to reach consensus on Solana, where and what that means is, let's say there are transactions, right? Transactions are being sent over, and the validators want to execute the transaction. We'll get into the detail of that in a minute. But the validator needs to execute, the transactions. That how they need to be able to vote on the correctness of the transaction, right? Because there are thousands of validators on Solana. I think 1,500 currently. So this transaction is to get all of them, and they need to vote for transaction if yes, include this block or to skip the block entirely. So this is a guys. This is a better it's code over here. Let me turn out the I trained heavily this morning, so I'm catching code. But yeah, I'll be fine. So okay. So I was saying it's a better way to reach a final agreement on the blockchain for what transactions, what block will be included, yeah. And okay, so this is basically how how it is working now. What Alpenglow is proposing. So a leader, so that means there's one validator node, one particular node, which is called a leader. Yeah. And that leader is currently it is like a leader can have 4 slots. That means you can be a leader 4 times before you are rotated. So that means you can we'll get to that. Let's take a step by step. So Alpenglow is proposing is once transactions get to the leader, maybe via other validators or a wallet is sending transaction to the leader directly. So the leader starts executing this transaction, starts signing the transaction with the but it gets a Merkle it creates like a Merkle tree, and we have a Merkle root for the transactions. Yeah, so you cannot be able to reconstruct transaction later. We'll get to that, but now we have these transactions, and the transaction needs to be broadcasted to other nodes, so other validators on the block on the network. Yeah, so that's how uh, that's that is still what was previously happening. Eventually, the transactions to get to other validators. But there's a peculiar thing about how Alpenglow fixes this. So when the transaction is being disseminated from the leader block to the leader validator to the other validators, there is there's something called because it does not just build the whole entire block before it starts sending it over. That will take time. So, want to increase latency, so reduce latency rather. So, as it starts building the transactions, as it start, it builds the transactions, it bundles them into slices. So, first slice, second slice, third slice until the full block is completed. So, and as you get the first slice, it broadcasts that first slice over the network through to other validators. Yeah. So and the slices are broadcasted in shreds. So it will this particular slice it will broadcast them in shreds. That's like a smaller unit of each of a single slice. So what and the important thing is previously it needs to be able to send this shreds over to every validator on the network. That's every 1,500 validator on the network. But that's a bottleneck on the leader validator because it needs to be able to send to all of them at once. So and if the validator network is capped at 1 gigabyte per second, how you see it takes it now is now the problem is now on the validator because the maximum its network can do is 1 gigabyte per second. It needs to transmit, let's say 10 let's say it needs to transmit 10 MB of transactions to every validator. So you see, if you divide that by 1 gig per second, it's the amount of time it takes for it to get to every validator at the same time. So that's the bottleneck that we're talking about. But what Alpenglow proposes here is, if you look at this, okay, before we go to it, let me just do a summary. What Alpenglow is proposing now is instead of making the validator broadcast the transaction to every node, you do broadcast this transaction to stick with nodes. So stick with uh, validators. It means stick. Is what it means here. Stick. So it means for you to be a validator, you need to have a stake in the blockchain. Like that means you have locked up some soul, so a big amount of soul before you can be a validator node. So it broadcasts based on the weight of your stake. It broadcasts more shreds to you. So once you get the shred, it just broadcasts it based on the amount of stake that you have, yeah, until it gets everything. So what now happens between the remaining validator is they now communicate to each other, they gossip over the network to say, okay, you're missing this part, you take this part, I have this part, you take this part, until every one of them builds that full slice, and it keeps going like that until a full block is done. But once they've built a slice, they keep the what they've built in something called block store. I'm going to get to that also. And so that's how it just goes. So by the heavy, if you have heavy stake, you are getting more transactions, more shreds. And one important thing about what they're proposing is, yeah, okay, it's already done, but it is something called erasure coding. Erasure coding means these transactions that are broadcasted for fault tolerance here. If there's any scenario whereby you lose some of the packets, you lose some part of the transaction, you can rebuild the transactions via other parts of it. So you can reconstruct the transaction. Basically, that's what erasure coding means. So it is erasure coded before it is distributed. The shreds are erasure coded and they're distributed over to stake with validators, which now gossip over the network about who has this part, who needs what part, and they build the whole thing. Now everybody now has the full what's it called, the full sample of the transaction. So of the shred, and it keeps going like that till you've gotten the first slice, second slice, until you have a full block where you now vote on the transaction on the block if you want to include this block or not. So the leader starts creating the block and is sending slices over in shreds to the other validators. The other validators, which are erasure coded, the other validators now communicate with each other. Okay, I have this part, give me this part. They share it within themselves. So that is utilizing every validator's computes, every validator's machine instead of putting the bottleneck on just the leader. The leader just broadcast it once, then everybody communicates with each other to get to what part do you have instead of the leader sending the full thing to everyone individually. Gets so that's basically what Alpenglow is proposing. So that part I explained is the rotor. That's how it distributes the transaction, the block. So now the voter is how how the voting actually occurs. Yeah. So this takes a minimum. How do you know what time it takes to finish to vote? So you get a minimum of the delay of this one is delay of 80% validators or two times the delay of 50% validators. That's what that means is. So it will take the two voting are going to be going on at the same time. So concurrently, it means we can either have this block included if 80% of the validators agree to include the block at a go. But if there's a reason why, for some reason, 80% of the validators are not online, that means 80% of the stake, not 80% of the validators, 80% of the stake are not online. So it's stake, not validator. Stake means if I have 40% stake, someone else has 30% stake, another person has 20% stake. Those three alone makes up 80% stake. So if 80% stake uh valid are online and they want to include that transaction, they want to include that block, it will pass. So that means 80% stake, not 80% of the of the validators. Yeah. So for some reason, if 80% of the stake not online, then we'll do at the same time. There's a two round of 60% stake going. So that means if we get 60% of stake agree to include this, first time we try again, we have another 60% agreeing to include the same block. So which of these condition, whichever of them is true for gets make the transaction work basically. So at the same time we're doing if 80% of the stake agree or if a two round of 60% of the stake agree. So now let's read what it says after I've done the explanation. Let's now read what it says at the 1 minute. Yeah, it says the voting component, that's the voter, finalizes block in a single round of voting if 80% of the stake is participating, and in two rounds if only 60% of the stake is responsive. So these voting modes are performed concurrently, such that finalization takes a minimum of a single 80% stake or two round 60% stake time after a block has been distributed. So that is how the voting. That's how the voting works there. Okay, so that is the abstract of it. And Alpenglow featured the 2020 resilience, wherein the protocol can tolerate access to condition. Yeah, these ones are just additional explanation to what is happening here. When we go into the everything, into the white paper, the white paper is JK is whining me. So the white paper is 52 pages, I think. Is 50 no, 49, 48, 47 pages long. Yeah, 47 pages long. Let's see how far we can cover. Let's go. So we are on page one now, and we've gotten through everything here. Upload, blah 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 blah. I think this is the word of. Okay, you might want to read this one up. I just want to. We've talked about most things, but we want to talk about the things that we've missed. This one is just saying if you are new to blockchain, understand why blockchain exists. That's basically what it's saying. You can let me see. I can get. Let me get this. Put it in the chat real quick. So it's good. Here you can see. Paste that in the chat so you can get it in the chat. Yeah. Yeah, I sent it in the chat on Telegram. That's on Twitter. It's one long URL, but you can get the PDF there. So this one is just explaining why there is a need for a blockchain, basically. So if they are proposing this to Web2 folks, because most of this, if you look at it specifically, most of these papers are people trying to just they don't think about things like blockchain. They just think about it like distributed systems. So it's not like a proposal for, even though it's for Web3 engineering, but it's not like a proposal that if you're a Web2 guy, you can understand. So this is what this is doing. So your introduction should be able to be other people should be able to relate with your introduction. That's what. So I think what's the word computer, but we call it blockchain, or what is it called? Yeah. Yeah, it's called the blockchain. Just explain what a blockchain is here, basically. So you can skip all this part, but if you still want to get about it, there are a lot of references for about where the the idea for this came about. You can click on all of this and to take you to the pages where it's cited. This one is from Benjamin Y. Chan and Raphael Pass. Simplex consensus. So there are a lot of references there, and I think there are a lot of references to Lamport also. Leslie Lamport is there. Yeah. Let's just continue what we're doing. So the overview. Okay, we can start here. Says let's provide the high level description of Alpenglow. And by the way, let me get JK's posts. I'll put that in the chat also. JK did a thread about what we're talking about now, so you can just read the TLDR. That's JK. Let me get that in the chat for a minute. I will get this is the TLDR 11K impressions. Copy link. And I will paste that here. So, disclaimer: if you think I understand exactly what I'm talking about here, think again. We're reading this together. But just yeah, I'm going through it together. Okay, let's see. Okay, I've dropped JK's tweets in the chats, so you can go over it if you want a TLDR. I think he did a very good job at explaining everything that's there. Okay, so back to what we're talking about. So Alpenglow is a proof of stake blockchain where each node has a known stake of cryptocurrency. We talked about this already. A time is partitioned into slots. Each time has a slot number and the executed leader from the set of nodes. We talked about this also already. Each leader will be in charge for a fixed amount of consecutive slots known as a leader window. So Alpenglow is not specifying what number of slots the leader will be in charge of the what number of slot the leader has, because that's not what basically what they want to do. They also want to tell you a better way to achieve consensus. Then the blockchain can determine if they want the leader to have 5 slots, 10 slots, 2 slots, whatever slots. Here's a proposal now to reduce the slots to 2 instead of 4. I think that proposal was passed. I don't know. You can look into that later. So a threshold verifiable random function determines the leader schedule. So you can know who the leader will be up front. You can know who the leader is next for the next epoch. You can know what the leader is the next 2 blocks, the next 4 blocks, you know what the leader is. When a node is a leader, it will receive all the new transactions, exactly what we talked about, either directly from a user or relayed by other nodes. So you can either get transaction from users or other RPCs that the users are connected to. Yeah. So those the validators can send the transaction to the leader, or the user send the transaction to the leader directly. The leader will construct a block with this transaction. A block consists of slices for pipelining. That's what I was talking about, chunks, slices. So, and immediately it's constructing the slices, it begins disseminating the slices over the internet, over the network. Sorry about that. The slices themselves consist of shreds, talked about it, for fault tolerance and balance dispersal. The leader incorporates the rotor algorithm. So we talked about the rotor algorithm is the one that helps the leader broadcast the transaction. So with erasure coding, that means it makes it easy to reconstruct the transaction, the slice, the shred, if some part of the it makes it easy to reconstruct the slice if some part of the shreds are missing, basically. So erasure coding is, let me get to that. Okay, this is a video. Erasure coding. I was looking, maybe we'll try to do an experiment to implement it here. This is a good video if you want to look it up. Erasure coding in action, how big they'll say petabyte of data. It talks about, let me see, get it back from ByteMonk. It talks about erasure coding. Erasure coding is just a method to let me just let him explain it instead. Can you hear? Let me get to, okay. I think this one. So there are two things involved in erasure coding. There's the parity and I forget the main data chunks and the parity chunks. So there's this formula that's k plus m to that's how you express it. K plus m, that's the number of data chunks and the number of parity chunks. If you want to get the ratio, you do k plus m over k. We'll get to that. Don't worry. I'm moving way ahead of myself here. It's just simple math. I want you to get to, okay. They said you have 10 MB data, you want to store it with the fault tolerance, so that means with erasure coding. So when some part of the data is missing, you can still reconstruct the full video back. So that's what it's trying to tell you there. Yeah. You can get this part to say split the file into chunks. Let's say K is 4, so you have 4 chunks of your data. Then you specify what's the parity I want for this data. Do I want it to, let me just let him explain there. Okay. And here is using m equals to 2 for the parity. That means you want 2 parity chunks extra for your four memory chunks, the 4 data chunks. So this is stored alongside the parity chunks, and there's a formula to recreate it and simulate that a transaction is missing. Some data is missing. I try to rebuild it back and get the exact same data. So let's just proceed. So that means you are storing more than you need, but you actually need that to reconstruct the whole thing. So four chunks of data and two chunks of parity because we are using k equals 4 and m equals 2. Yeah. And with this, you can reconstruct if you have two part of this data lost. You just need you can use the two. You just need if you have two part of it lost, you can still reconstruct the old data back. That's what this one is saying. Yes. So let's continue the video. Let me increase the speed. Yeah. So it means it's saying what I forgot was the number of parts is 4, right? And number of chunks is 2. So if you have a total of 6, you only need 4. You only need 4 parts to build the whole transaction part. And the 4 does not necessarily have to be the 4 data part. It might be two data parts and two parity or whatever however way it will be. So the more parity you have here, the more fault tolerant your data storage will be. So that means if you have four data chunks and you have three parity, so that means you just need just four out of seven to reconstruct this data back. If you have four parity, you need just half. That means if you have four data chunks, I have four parity chunks. You need just k. That's four data. So it might be the whole four parity chunks that you have there. I'll be able to reconstruct this data back. So the data chunks and the parity chunks are the two important things for erasure coding. We can actually do a demo of that. We can write it. I think it did a Python example, but I'll show you what that looks like in Rust in a minute. So you by inference, you know that you are storing the data is actually four chunks, but you need two parity chunks. You are storing 1.5, so that's 1.5x storage instead of storing just one size. You are storing 1.5 size. That means you are sending over for our case, we are sending over 1.5 size. If we're doing a four data chunks and two parity chunks, but if it's twice, if we're doing four data chunks and four parity chunks, that means we're sending over twice the size of the data we actually need. But if half of that data is lost, because we have half, we can reconstruct the whole thing. That's what erasure coding just basically means. So this one here is also same thing. We have six data chunks and we have three parity chunks. Total chunks is 9. You just need 6 out of the whole 9 chunks to reconstruct everything. For this one, you have 4 parity chunks, 8. You need just 8 to reconstruct the whole thing. So the more parity chunks you have, it will determine how much extra sizes you are transmitting. So let's just continue. Yeah, yeah, yeah. Okay, this is one simple example of how he's explaining it. So he has 5928. Let me see. Yeah, 5928 is the full data he wants to store. And he adds two parity chunks to it. So it's now saying he stored two extra numbers calculated using a simple mathematical rule. So parity one is 5 plus 9, that's 5 plus 9 plus 2 plus 8 equals 24. And I have a 5 times 2 plus 9 times 8, that'll be 82. So you're storing 5, 9, 2, 8, 24, 82 together. So if four of the chunks are lost, let's say 2, 8, 24, 82 are lost, you can reconstruct the whole thing again. That's basically what erasure coding means. So that's how your transactions are saved in real life. So if by any means the transaction gets dropped, a packet is missing, with erasure coding you can reconstruct. So I'm dwelling more on erasure coding basically. So let's get MC. Yeah, blah, blah, blah. Yeah, so this is an example. Okay, okay. So it's saying P1, P2 erasure coding. So if two of these data is lost, you can use the parity chunks to reconstruct the parity chunks and some of the data to reconstruct the full lost ones back. So that's cool. You have D1, D2, D3, D4. Then with that formula that you talked about, you derive the P1 and P2. So now I have a D1, D2, D3, D4, then P1, P2. So if D1 and D2 gets lost, you can use P1, P2, D3, D4 to reconstruct D1, D2. And if D3, D4 or D2, D4 gets lost, you can use P1, P2, D1 and D3 to reconstruct the whole thing. Yeah. Yeah, let me forward it. Yes, this is an example in Python. I'm not a Python person, but I'll try to understand what's going on here. Okay, so he has this RS. There's this package read Solomon. Is the algorithm, that they use for this erasure coding. I'm betting he was the inventor of it. So this is a Rust great read Solomon erasure v6. If you search erasure, you would see read Solomon erasure, Solana read Solomon erasure, fast erasure, shake, DECD, erasure coded data. So there are different crates that you can use for erasure coding on Rust. In Rust, so I'm looking at this read Solomon erasure 6 because that's 4 million all-time downloads. So that's good. And so let's just look at it. Okay, read Solomon erasure. This is how it looks like in Rust. Let me use Rust that we're familiar with. If you're familiar with Python, you can, you can use Python. Restore more erasure. You add it as your import the crates in your dependencies, whatever version you want to use. You can use this SIMD. You can read this up actually. Let me share this in the chat also. Chat here, live chat here. Yeah, sent. So this is an example. You have use the macro shards and the read Solomon one. So we okay. So this is you say let R is read Solomon new, three shards and two parity shards. Three data shards and two parity shards. You remember what data shards and parity shards are, yeah? So you're saying I'm constructing this R, which is an instance of read Solomon, just three data shards and two parity shards. Then use the shards macro. So these are the four data bytes that we have, whatever data bytes should be. And these last two are the parity shards. So let's assume the parity shards here is zero bytes. So we say encode, there's this encode function on R. That's an instance of Rich Solomon. So R dot encode master copy, which is this one, the unwrap. I've encoded it. So now I want to make a copy and transform it to an option shard. So if you do master copy the iter the clone the map the collect, so just copying these shards that we have here, uh copy and transform it into option shards arrangement. So we're copying the shards from this uh master copy. Then we're saying want to delete position 0 and position 4. We can remove up to two shards, which may be data or parity shard. So it might be either data shard or parity shard. You can remove anyone. So anyone may be lost. Anyone may be lost. And we're saying we want to intentionally make this none to remove the values there. Yeah. And we want to reconstruct. So now we see that there are two shards lost. So now reconstructing it with the shards that we have. Now we said index 0 and index 4 are lost. So now we have just 1, 2, 3. Yeah, we can only have K. You have just three shards and we're trying to reconstruct. And we are set. So just do immediately we reconstruct, we'll get something back. So we'll now try to we get something back inside shards. So now try to collect what is inside shards now and see if it matches when we do result out of verify result. They want to assert that master copy is now the same thing as result. Yeah. No master copy. Yeah, we popped out this 0 and 4. and we are reconstructing it. Yeah, right. So now at the end of it, we should have master copy and result same thing. Now we should have uh this old data shards back. So that's basically how erasure coding works. You can test it out, you can copy this and run it. Well, that's how it works. So let's get back to that's erasure coding. So that's how the shreds are disseminated over to other validators. So like I said, it wants to utilize the total outgoing network bandwidth in a stake fair way. Okay. So in a stake fair way, if you have more stake, you're going to get more more shreds to disseminate. So that way you're not putting load on the leader nodes. You're not putting load on the leader validator. The bottleneck will not have to come from leader validator's network. Everybody has to gossip over the network and get the remaining of the data. So as soon as the block is complete, the next leader will start building and disseminating the block. Next block. Yeah. Like I said, the shreds and slices of the incoming blocks are stored in block store. We'll talk more about block store in section 2.3. So this one is like an explainer. We'll be talking about it all week, hopefully, all week. So not all week, maybe like 2-3 days in this week, or like 2 days in the week. So there's still time to go over everything. So let's just see how far we can go. Maybe we can get to fault tolerance. All of this is just majorly re-explaining what we've the general overview. So that's what the white paper is giving you a general overview of what this is about in introduction and abstract. So now we're getting into the meat of it. It's basically what's happening. So let's start here. We've talked about this, study data structures in place, we discussed the voting algorithm. Talked about the voting algorithm. So a single round of 80% stake or 2 rounds of 60% stake. I mean, it's okay. So let's see. Back I actually said the vote. Skip it back. Okay, so yeah. So it's just basically what we've talked about. Nodes will then vote on whether they support the block. So we introduce different type of votes in section 2.4. When we get there, we talk about the types of votes and certificates. So with all the data structures in place, we discuss the voting algorithm. That's voter, section 2.6. If the block is constructed and arrives in time, a node will vote for the block. If a block arrives too late, a node will instead vote to skip the block, since either the leader cannot be trusted or the network of the leader is unstable. If a super majority of the total stakes votes for a block, the block can be finalized immediately. That's 80% or 60%, 2 rounds. However, if something goes wrong, an additional round of voting will decide whether or not to skip the block. Yeah. So discuss the logic of creating block as leader. So this one is very important, interesting. Talk about the logic of creating blocks as a leader and how to decide on where to append the newly created block. Finally, in section 2.0, we discuss repair. It's very important also. How a node can get missing shreds, slices, and blocks from other peers without gossiping. But now, repair helps nodes to retrieve content from an earlier block. So let's say there's a previous block, and for some reason, you're not able to construct the full thing. You can repair and get the content from an earlier block that they might have missed, which is now an ancestor of a finalized block. So this completes the main parts of our discussion of the consensus algorithm. So this is consensus algorithm. So this one is trying to prove the correctness of Alpenglow. If you are interested in that, you can look that up also. Blah 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 blah. Failure handling in section 3. This one is explaining how. Let us get to this part already. Fault tolerance, safety, and security are the most important objectives of any consensus protocol. We know that. So now they are comparing other previous proposals This is the BFT one, I think. I think it's this one. Let me see. It should be scroll down. Marshall C. and Robert E. Shortcut. Yeah, Leslie Lamport. Reaching an agreement in presence of four. Yeah, but if you are interested in that, you can just search this exact thing up online and you get. Let me just show you. Can come here to new tab, paste it, search, and you get this paper. This exact. I'm not a robot, bro. So you can get this. That's this the exact paper. Yeah, I can get that page 22, 228 to 234 page. So yeah, but yeah, let's get back to what we're talking about. These are all trying to compare why Alpenglow is important. So the first assumption of Alpenglow, so Byzantine nodes as faulty or malicious nodes, we assume that for Alpenglow to work, the malicious node must control at least so a maximum of 20% of the stake. That means it cannot be, it must be less than 20% of the stake. So the remaining nodes controlling more than 80% of the stake are correct. So we are assuming that 20% of the stake, less than 20% of the stake is Byzantine node. Then the remaining nodes, 80% of the stake are correct. So that means we will have our 80% first round of voting successfully. That's the first assumption. Uh, Assumption one is enough to ensure that even an adversary completely controlled network cannot violate safety. A network outage or partition would simply cause the protocol to pause and continue as soon as communication is restored without, yeah. If the network is not being attacked or the adversary does not leverage some network advantage, Alpenglow can tolerate an even higher share of nodes that simply crash. Remember, so that means we have 20% of malicious nodes. It can still tolerate another 20% of, let's say, inactive nodes. Yeah. So 20 are malicious, 20 are inactive. Then the 60% stake, that 60% stake will pass because we have two rounds of 60%. That would pass. That's 40, 60. Yeah. Let's see if that what it's talking about. Apple can correlate an even higher share of nodes that simply crash. We intuitively explain the difference between assumption one and assumption two as we sketch out English correctness. So assumption two, extra crash tolerance. Byzantine nodes control less than 20% of stake. So other nodes with up to 20% stake might crash. The remaining nodes controlling more than 60% of stake are correct. So that is assumption two. Like I said, the first time was if you can have a single round of 80% stake votes correctly. And the second one is you can have two rounds of 60% votes correctly. So that's this one is still fine with that assumption. Uh, Performance metrics. This explains what I just talked about here. So 80%, then two rounds of 60% time. In a nutshell. So this delta pi, yeah, is a network delay between a stake width fraction pi of nodes. Blah 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 blah. Yeah, this is just re-emphasizing to achieve this finalization time. We run an 80% and a 60% majority consensus mechanism concurrently. So it's not like the 80% one goes first. Then if it fails, we revert to the 60% one. No, both are running concurrently. Whichever is successful first, yeah, will make it pass. Yellow latency 60% majority cluster is likely to finish faster on a two iteration path, whereas more remote node may finish faster. It's just explaining. One pinpoint blah 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 blah. Yeah. In Alpenglow, we strive for simplicity whenever possible. While simplicity is difficult to quantify, it remains highly desirable. I think for robust systems, it needs to be very important that they are simple. Because when something is robust and it's complex, you cannot maintain that system. It needs to be simple and straightforward. You can build on top of that simplicity instead of building on top of something complex and you cannot easily modify or maintain or point out the fault in it. A simple protocol can also be upgraded and optimized more conveniently. Exactly, that's good. Related work. This is also looking back to previous proposals and the brother of Alpenglow. I think that is in. It's called K something. I can't remember. Is it Kuvu or Kudzu? Okay, Kudzu is an Alpenglow academic sibling. That is, it's most of the proposals are exactly the same. Most of the assumptions are similar with a similar theoretical model. But the part about Kuzu is that Kuzu is more efficient in a permissioned environment. Yeah, this is Kuzu is specified for a permissioned model, not a decentralized model. Yeah, so Alpenglow features leader windows where this one is just really explaining everything. Just the thing is, if you're talking about something as interesting as this, you don't want to say it once. You want to repeat and go over things so you actually feel what you're talking about. Yeah, follow up work, hydrant, yeah, say protocol, blah blah blah. Okay, now this is the important part. Not important, but every part is important. But these are things that I should want to know about. Names. We introduce various objects in the form of name, XY, which means the name is deterministic encoding of the object type name, blah blah blah. Epoch to allow for changing participants and other dynamics. The protocol rejuvenates itself in regular intervals. The time between two such changes is called an epoch. Epoch, 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 bro. You get me? An epoch, epochs, epochs are numbers as E equals 1 to 3. See, the participants register or unregister 2 epochs earlier. So you cannot just opt out of validating or voting during an epoch. We need to know 2 epochs before the time, i.e., the participants and their stake of epoch E plus 1 are decided at the end of E minus 1. So let's say the current epoch is E. For you to be a part of the this E, you must have signified that you want to be part of this epoch 2 epochs before. So that's E minus 1. That's just what you're saying. I decided at the end of E minus 1, a long enough time before E plus 1 starts. This makes sure that everybody is in agreement on the current nodes and their stake at the beginning of E plus 1, because all nodes need to know as what's happening in the other nodes because they communicate with each other, right? So you cannot just jump into the middle of a conversation. You cannot interrupt. So they need to know everything about you. That's what is explained in node. We operate on n individual computers, which are called nodes, V1, V2, Vn. The main job of nodes are to send or relay messages and to validate blocks. Because of this, nodes are sometimes also called validators in this literature. While the set of nodes changes with every new epoch, as mentioned in the previous paragraph, the nodes are static and fixed during an epoch. Yes, you don't interrupt the nodes. The set of nodes is publicly known, i.e., each node knows how to contact via the IP address and port number of every other node. So they know the IP address and the port number of every node. Each node has a public key, and all node knows all public keys. So all nodes know the public key of each other and they can communicate with each other. Yeah. The information of each node, the public key, stake, IP address, the port number is announced and updated by including the information in the transaction on the blockchain. This guarantees that everybody has the same information. Currently, Solana has 1,500 nodes, sounds correct. But our protocol can, in principle, scale to higher numbers. However, for practical reasons, it may be beneficial to bound. It'd be beneficial to have a max. So n will be less than or equal to n max. Where max is not specified in this yet. Messages. Node communicates via exchanging authenticated messages. Never uses large messages. Yeah, so specifically, all messages are less than 1,500 bytes. Because of this, we use UDP with authentication. So either quick UDP or UDP with a pairwise message authentication code. So UDP, how they communicate. Use UDP with authentication. So either quick UDP or UDP. You can get into that later if you want to. If you want to talk, if you want to research about UDP, yeah. But yeah, it's just a short 1 hour something to talk about Alpenglow. We'll soon be done with the live stream. I know it's boring for some people already. Broadcast. Sometimes we don't need to broadcast the same message to all n minus one other node. So the sender node simply loops over all other nodes and send the messages to one node after the other. Despite this loop, total delay is denominated by network delay with a bandwidth of 1 gig per second. Transmitting 1500 shreds takes 80 milliseconds, well below the average network delay of about 80 milliseconds. Yeah, I was listening to, was it, I can't remember the guy's name, from Double Zero, and was like, NASDAQ do not send the current price a, of let's say a stock or something to every machine. Yeah, NASDAQ just broadcasts it and the machines pick it from wherever it's broadcasting to. That's what Double Zero is doing. So now they know Alpenglow knows that even though it's not 80 milliseconds is not really a problem, yeah. But to get 80% of the total stake, we need to reach approximately 150 nodes, which takes about 2 milliseconds. So that's at least 2 milliseconds. But voting messages are shorter and hence need even less time. Moreover, we can use a multicast primitive provided by an alternative network provider like Double Zero or Skion. Is it Xion? So if you still feel in 2 milliseconds can be shorter, you don't want to send to everybody at the same time. You can just broadcast it and everybody picks it from wherever they're speaking to. So I think that's what Double Zero does. Not sure. I think that's what they do. So stake. Each approach or the stake now. No, not stake, yeah. So each node has a non-positive stake of cryptocurrency. Yeah. You need to lock some cryptocurrency. That's basically what this is saying. Yeah. So and how do we know when they say stake with validator? The stake of a node signals how much the node contributes to the blockchain. If node 2 has twice the stake of node 1, node 2 will earn roughly twice the fees. And moreover, node 2 also has to do twice the outgoing network bandwidth. Like I said, if you are getting from the leader, you still have to gossip to to everybody on the network that needs that part of your own what's it called? That part of your own slice. Yeah. However, all nodes needs enough in bandwidth to receive the blocks and some minimum out bandwidth to distribute blocks when they are a leader. Time. We assume that each node is equipped with a local system clock that is reasonably accurate, e.g., 50 ppm drift. We do not consider clock drift in our analysis. This is not what they're talking about here, but it can be easily addressed by incorporating the assumed drift into timeout period. I think Readily one sent a post about this. Someone was trying to fix the clock, sort of the proof of history clock. It was trying to do something different with, I can't really remember. I was trying to see if I can get trying to fix the clock issue. So by incorporating the assumed drift into timeout periods, clocks do not need to be synchronized at all for this to happen, as every node only uses its local system clock. That's what I'm saying. So each epoch is partitioned into slots. A slot is a natural number associated with a block and does not require timing agreement between nodes. That means just a number associated with each block. So the time period of a slot could start and end at different local time for different nodes. Nevertheless, in normal network condition, the slots will become somewhat synchronized. So saying they don't really care about the time on this, on the block, because it will still, in normal network condition, the time will still be synchronized. During an epoch, the protocol will iterate through all the slots, slot 1, slot 2 to L, And Solana's current parameter of L is 432,000, which is possible, but much shorter epoch, example 18,000, could be advantageous. For instance, to change stake more quickly. But no, we don't want to do, we don't want to do that. Each slot S is assigned a leader node given by the deterministic leader function, which is known before the epoch starts. So a leader just explain every component of it. So each slot has a designated leader from the set of nodes, and each leader will be in charge for a fixed amount of consecutive slots known as the leader window. Yeah, that's you'll be in charge of a fixed amount of slots, consecutive slots, known as the leader window. And a threshold verifiable random function is evaluated before each epoch to determine a publicly known leader schedule that defines which node is the leader in what slot. So you will know when is your time to be the leader if it be your time. Timeouts. Our protocol uses timeouts. Note set timeout. A protocol gets waiting forever for specific timeout are based on global protocol parameter delta, which is the maximum possible network delay between any two correct nodes. Blah, 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 blah. Timeout durations can be changed dynamically based on conditions such as the protocol is correct irrespectively of delta exhibited by the network. For simplicity, we conservatively assume delta to be a constant, e.g., 400 milliseconds. Importantly, timeouts do not assume synchronized clocks. Yes, so that's I was trying to say we don't even want to care about clocks right now because it's not important to us. Instead, only short period of time are measured locally by nodes. Therefore, the absolute world clock time and clock skew has no significance with protocol. Each extreme clock drift can be simply incorporated into the timeout. Example, to tolerate a clock drift of 5%, the timeout can simply be extended by 5%. As earlier explained, as later explained, Alpenglow is partially synchronous, so no timing or clock-related errors can derail the protocol. That's what I'm saying. That's what they're saying, that Alpenglow is clock error proof. So that's not clock error cannot affect what Alpenglow is trying to propose. So it's just a lot of good stuff, a lot of good stuff here. To explaining what adversary means. So some nodes can be Byzantine in the sense that they can misbehave in arbitrary ways. Byzantine node can, for instance, forget to send a message. They can also collude to attack the blockchain in a coordinate way. Some misbehavior, it is signing inconsistent information, may be provable offense, while some other misbehavior cannot be punished. It is sending a message late could be due to an extraordinary network delay. So yeah, that one you cannot actually punish because it might be a network delay on the validator's end. So in assumption one, we assume that all Byzantine nodes together own strictly less than 20% of total stakes, and up to an additional 20% of stake may crash under the condition described in section 2.11. So the remaining nodes are correct and follow protocol. For simplicity in our analysis, we consider a static adversary over a period of one epoch. So asynchrony, consider the partially synchronous network setting of global standard time. Messages sent between correct nodes will eventually arrive, but they may take arbitrarily long to arrive. We always guarantee safety, which means that irrespective of arbitrary node delay, arbitrary network delay, correct nodes output the same block in the same order. All this is just story. However, we only guarantee liveness when the network is synchronous and all messages are delivered quickly. In other words, correct nodes continue to make progress and output transaction in periods when messages between correct nodes are delivered in time. In time, just in time. In the model of GST, synchrony simply corresponds to a global worst case bound delta on message delivery. You can get into all of this. So hash functions. Okay. I think I'll just stop here for now. This has been eye-opening for, and it's interesting actually to go to deep dive into how what Solana will be working off of So that way you can position yourself, know where how things are working when you start to contribute and all. So for now, what have we learned so far? What have we learned so far? We learned how the blocks will be made, how it will be transmitted, what erasure coding is, how they can reconstruct the blocks, reconstruct the slices if some parts are dropped or missing. And yeah, been cool so far. And unfortunately, this is where we'll be stopping for now. They'll meet on Wednesday. Yeah, so just a short 1 hour of going over Alpenglow. Thanks, guys. Thanks for jumping on. And this has been the Anchor founder. Peace. Yeah, yeah, yeah.